tutorial, a virtual observatory tutorial, which will last for 2 hours and will be presented by Fran Jiménez-Esteban. So Fran, Fran is a member of the Spanish Virtual Observatory since 2008. He is an expert in the VO and in the scientific exploitation of databases and archives through the VO. He has large experience teaching VO tools since he regularly organizes VO schools at European level. So welcome, Fran. The floor is yours. We can see your screen. We cannot hear you.
Can you hear me now?
Yes.
You can hear me now. Okay. Okay. So I'm going to share the screen again. Okay. So thank you very much for the introduction. And as Isia has said, today we have 2 hours of tutorial. The idea of this tutorial is to introduce some virtual observatory tools. You have already this morning has been already a talk about the virtual observatory, so you know more or less the general idea, the general concept of the virtual observatory, and now the idea is to put our hands on the computer and to start using the data. Okay, so I have prepared three tutorials for 3 different tools, for Aladdin, Topcat, and Vosa. The tutorials has been already sent you by email, so you have the tutorials, and the idea is that you follow the tutorials, and I will at the same time I will explaining the different steps. So I will give you time to do the tutorials, and after a few minutes I will do some of the steps, and you can continue working on the tutorial, and from time to time I will explain different things, and I will show how to do the tutorial, how to do the different scientific cases. We have also the help of 2 other members of the Virtual Observatory team, the Spanish Virtual Observatory team, which is Patricia Cruz and Miriam Cortez. They are going to be available through the Slack channel. So if you have any question, just put on the channel, and we will answer your questions. So don't get stuck on the tutorials. If you have any problem with the tutorial, just put the question in the Slack channel. Okay, so I hope that you have already prepared the software that we need, which is Aladdin, Topcat, and Vosa. Vosa, you don't need any software, it's just a web page, so but you have to register on Vosa. So we can start then with the tutorial. The first tutorial is about Aladdin. Okay, so I have also split, you see my screen, I have a split into parts. At the right, I'm going to open the different tools, and I made the different exercise, and at the left I open the tools, and at the right I will have always these presentations with the different steps that we are going to follow. Okay, so as I have said, the first tool is Aladdin. Aladdin is a sky atlas developed by the CDS in Strasbourg. So Aladdin is a software that allow to query different image archives and also catalogs. So we can combine the images with the catalog data, overplot it, and do different steps with or different tags with the tables and catalogs, like from match tables, filtering sources, and all these things. That this is more or less what we are going to do. The exercise or the scientific case that we have prepared is about the brown dwarf. Just to put into concept, everybody know about the brown dwarf. He's in the evolutionary stages in between stars and planets. So they are the faint objects. They are nearby sources, and they present a red color because the low temperature. So this is the physical characteristics that we are going to use to apply different filters to the catalogs. Okay, so let's get started. The first thing that we have to do is to launch Aladdin. So if you have your tutorial, open the Aladdin tutorial and let's start working. This is the workflow that we are going to follow. It's 5 steps. Okay. The first step, of course, is to launch Aladdin. So Aladdin is just a Java hard file that we have to launch with a Java command. So you can see at the right side, I have a console. So here I have different Java files or different PO tools, and just we are going to launch Aladdin. Okay, so here we have Aladdin. This is the main window of Aladdin. That's, as you have seen, Aladdin is divided in 3 different regions. The left side, which is the discovery area, where you can see the different catalog accessible. Here at you can see that there is almost 28,000 different archives that are now accessible through the tool. You can display the different trees and see the different archives which are available for images from catalogs, databases, etc. Okay, so this is the first thing. I will give you then 3 minutes to continue with the following step, just following the indication of the tutorial. Okay, the following step is to discover the data in a radius around this area. Data in the 2MAS catalog and in the Sloan DR12 catalog. Okay, there is no question on the Slack. So I guess that everybody has been able to open the Aladdin and start working with the tutorial. So if you don't know the tool, I think that the tool is very intuitive, at least to start working with the tool. So you have at the top, you have different menus to open different files. You can work with remote data accessible through the VO, or you can also work with your own data. There is also menus to work with images, with catalogs, to overlay different things like coordinates, grids. And there are many options. So it's a very powerful tool and very useful tool that is worth to know. So at the center we have the image. We can show a single image, or we can also split the image region and load different images. As you can see, the upper image is Tomas, the bottom image is the DSS. We can match both images to show the same region. Okay, so but this is not on the tutorial. Let's follow the tutorial. Okay, so at the right side there is the plane region, where now we have two planes, one with the Tomas image, the other with the DSS image. Let's remove the DSS and keep only the Tomas. Go back to the single view. So let's download the data of the Tomas catalog in this region of the sky. Okay, the region that is defined by these coordinates. So here we are going to put in at the left side, we put in select Tomas, and we have here. Let's go to the catalog. We can see here that the Tomas catalog is accessible, and then we had to put the coordinates. And 40 minutes allowed. No. This has not downloaded the region. I don't know. Let's repeat the process. Auto 30, 0 plus 01, 30 and 40 minutes. Unload. Okay, and now it has worked. I don't know why the first time it hasn't worked, but now we have 683 sources from the Tomas catalog in this area, in the region of the sky. The coordinates are located at the top, are the coordinates of the region. You can see at the top of the central part, the central window. So the next is to do the same, but with the Sloan 12. There's the catalog. Do the same. Mm, 40. Load. Okay. So here we have already download the data from Tomas and from Sloan. If you put the cursor on the plane with the Sloan data, at the top you have some information about the sources, the range is optical range, about the sources loaded is more than 12,000 sources, the total sources available, and this. So the next step is to cross match the two tables. Okay. So I give you a few minutes to follow with the following part, which is the cross match, and I will go back in a few minutes to do the cross match, to show you how to do that in case you have not succeeded. Okay. Okay, let's continue with the tutorial. So we have downloaded the data from the TUMAS and the data from the SLOAN. TUMAS is an infrared survey. Most of you are already known, and the SLOAN is optical. The idea is to combine both surveys to identify the white dwarf. So we have to cross-match both tables. Okay. You can see now that if you open the catalog menu, now the different options are available. Options that were not available before when I shown the different menus. But now we have the options available because we have tables charts in the tool, which so we can perform different different tags with the tables. So what we want to do is to cross match the tables. First, we're going to put the TUMAS table, and then the second. There is also, if these names are some kind of encrypted names, are not really clear names, you can change the names of the planes, clicking on the plane, and then on properties. Open the properties. We can put here, which is this is TUMAS catalog, which is more clear. And here we have the options to put. This is the SDR12. Apply. Close. So now on the catalog cross match tool, we can cross match. Well, close this. Let's open again because now we have the TUMAS table. Now we have the names that we have put. So we put the tables. As you can see, the Aladdin has already identified the columns with the coordinates, with the right extension and the declinations. These data are included, or this information is included in the metadata of the tables that we have downloaded. So the tools understood perfectly the tables and identify the columns with the coordinates. We're going to put this such reduce and use the best match. There's different options, the best match or all matches, also without matches. And even you have different advanced options to do your advanced cross match. So do the cross match, and now a new plane has appeared with the sources in common. So here is the TUMAS sources in red. Now the SLOAN sources in blue. Now the sources in both catalogs in orange. Okay, so the next using the different criteria from the SLOAN catalog and from the using the SLOAN data and also the TUMAS data. I give you a few minutes to there is a question in the Slack channel by Siska that has obtaining more sources in the cross match than there are in the two-mass search. This is because you have put the first table, the Sloan table, and the two-mass table, the second table. So Aladdin has assigned one two-mass sources to each of the Sloan sources. If you the cross match put in the two-mass sources before, then the number of sources in the cross match will be lower. So please, Siska, try to do the cross match, put in the two-mass table the first one, and then the Sloan table the second one. Because the cross match is not symmetric cross match. What has happened is that probably a single two-mass source has been matched with more than one Sloan source. Okay, so let's continue with the filtering. Open again in the catalog menu. We are going to create a filter. This filter, you can put the name that you want to the filter. There is some filters already predefined, like draw circles proportional to the object luminosity, draw proper motion of stars. And also you can create your own filter. In this case, we are going to create our filter using the data from the tables. So in columns, we're going to use columns in slot tables. And here we have 3 sets of columns corresponding to the 3 different tables that we have. The original table from Tumas, the original table from Sloan, and the cross-match table. In the cross-match table, actually, is the columns from the other 2 tables. So in the cross-match tables, we're going to select the class column, which is a flag provided by the Sloan catalog that tell you whether the source is classified as a star or not. And the source is classified as a stars give the number 6. So we apply this. This is the expression for our filter, and we have to put the draw command at the end. Otherwise, the filter is transparent. So we apply and we export. Let's close all this. And now we have a new plane containing the sources which has passed the filter. From the original, which are 679, we have now 649 sources, which has this flag class equals 6. Okay. The following filters apply to the magnitude in the Sloan catalog. Actually, magnitude U larger than 22 and magnitude G larger than 22.2. That means that this sources has not been detected. So it's the filter that we're going to put. A new filter. New. Here you can see different buttons at the right side of the central window, which are shortcut to the actual menu here. So clicking on filter, we actually open the filter window, so we can define a new filter. In this case, now we have 4 set of columns corresponding to the 4 tables. I have a problem with the window, which is actually the zoom up menu provide me to get to the top of the window, but I think that I can manage with this. Okay, so we have to operate on the last table, which is the filter 1 table, and we are going to use the magnitude in U, which is here, and say this has been larger than 22.5, and also the G, what is G here is larger than 22.2, and also I'm going to apply infrared colors threshold in the that has been defined by Burgasser et al. In a paper of 2000, that are the criteria to identify brown dwarf. So we are going to also to put the G magnitude minus H magnitude lower than 0.3, and the G magnitude minus K magnitude lower than 0.3. And again, we have to put the draw command. Okay, apply. Let's close this, and I have an export. I forget to export the filter. Close. Let me open the filter. This filter. Let's open the properties, apply an export, and now we have the new table that contains only one source. Okay. The source actually at the bottom, at the center bottom, you can see the information about this source. Okay. You have the data with the coordinates, the two-mass name. So the last step of the tutorial is that just to look for information in Simbad. Okay, this is an already known white dwarf, so should be information in Simbad. So I give you a couple of minutes. Okay, let's finish with this. Just putting the cursor, placing the cursor over the source. Simbad information should appear. If it doesn't appear, just clicking with the mouse and click on astronomical object exploration, Simbad, and now we have information from this source. Okay. If you have realized at the right bottom corner, the SCD of the source has been shown. This comes from different data from different surveys, from Tumas, from Spitzer, from Wise. So here we have the SCD of the source. Also, clicking on the name. One second. Let me put here the browser. If you click on the name, then it goes directly to the page in Simbad for this source. Okay, so I'm going to stop here the tutorial of Aladdin. The tutorial that you have continues with different cases, different exercises, but we don't have time to continue with this. I want to move on to TopCat and then to Bossa. So I left you the different exercises for you to do it when you have some time and explore by yourself the different tools. You have questions, you can put it on Slack if you do it during these days, or you can also email me for any question that you will have with the tools. Okay, so let's close then Aladdin. And close also this tutorial. Before ending this tutorial, look here. I have some information. You have here the mail of the group, so you can ask for support in this mail. Also, you have here the web page of the group on different canals to be informed. And also at the end, I have put the link to a YouTube, a video in YouTube explaining this tutorial from the beginning to the end. The only thing that the tutorial is in Spanish, but I'm sure that with the paper of the tutorial and the video, you can complete the tutorial without any help. Sure. Okay, so the next is not Bossa, is TopCut. TopCut. This is going to let me see. There is okay. Regarding so let's continue then with TopCut. Let's introduce a little bit TopCut. TopCut is a tool especially developed by, for the work with tables and catalogs. Okay, it's a really powerful tool. It's really useful tool. I have to say that I use TopCut every single day, except the non-working days. But really, it's a tool that has a lot of power. Not only permit the query to all the different catalogs which are accessible through the VO, but also to work with the tables, cross-match tables, filtering tables, make subset, permit to explore the data by plotting one dimension graph, 2 dimension, 3 dimension graph, permit also to do a statistic, even has the possibility to use ADQL for querying in different services like Gaia, for example. Of course, we don't have time to follow or to explore all these possibilities, and this is just a small introduction of the tool. But it's very nice if you start to work with the tool. You will see how powerful it is and how useful it is. Okay, so the exercise that we are going to do, we are going to identify the sources belonging to the players catalog, players cluster, and obtain the distance to the cluster. Okay, so for this we are going to use the Digas data. Mind the Digas data, that, as you know, was the first data provided by Gaia mission with Parallax. Okay, so the first, we need to launch TopCut in the same way than before, with the Java -jar TopCut, and here we have the tool. Okay, so you can see there's as equally done before. We have different menus. You can explore different menus, different possibilities of graph, operate with different tables. We can do internal cross-match, pair cross-match, triple, quadruple, quintuple cross-match. Work with the different windows, do concerts or explore using the table access protocol query, multi-con searches. It has a lot of possibilities. Okay, so start then working with the tool. The first thing that we are going to do is to discover the Digas data. Just downloaded the data from the Digas catalog containing in a circle around the Pleiades cluster with a radius of 5 degrees. Okay, this is the first thing that we are going to do. I'll leave you a few minutes. Okay, so let's continue with this tutorial on TopCat to get the distance to the Pleiades. So the first thing is to obtain data from the Digas catalog. So we perform a cron search. We write Digas in the keyword and look for services. There are many different services providing data from Digas catalog, and we are going to select the ID Gaia provided by the German Virtual Observatory group. We can put the name of the object that we want to study, and when we click on resolve, TopCat connect with the Sesame service that provide the coordinates for this source. So we select the set radius, or the radius for collecting the data, and verbosity we can select 3 options: minimum, normal, and maximum. They are the minimum number of columns provided by the service, the normal number of columns, or the maximum number of columns provided by the service. This is defined by the service. I usually select maximum. I prefer to have columns that I'm not going to use. That doesn't bother. That in the following step has a column that I need, and it is not in my table. Okay, so this is the number of sources that we get. It's a different number of sources that the number of sources which are in the tutorial, and this is because the coordinates provided by the Sesame service are slightly different now than in the past when we create the tutorial. But it's just a difference of 4 sources, so there is not a problem for our case. Okay, so now we have our table. We can explore the table with in these buttons are also shortcut to different options in the menus. So here in the 4th button, we can open the table and explore the data. We can scroll down. We can, if you click with the right button of the mouse, then you have different options. You can short the data upwards, or you can short the data downwards, or even hide the column, or also very interesting, you can, for example, search in this column. For example, you want to share some source in particular, just write the name, which, let me see, for example, this is the beginning of the name, and then go directly to this source. Okay. In the 6th button, we display the metadata. Here we have information about the name of the column, the information that contains, the type of data, the unit, and also the UCDs, which are BO codes that tell the tool which data are in this column, these UCDs. Okay, so next step, identify the objects which are moving with the same or with similar proper motion. Okay, so as the cluster as sources which are has been formed together, they have all of them has similar motion in the sky, so they will have similar proper motion. So to identify the sources from the cluster, the sources from the cluster that the sources from the field, the field stars, we are going to select the sources that has a similar proper motion. Okay. Okay, let's continue. So we go to the graphic and create a plain plot, or also here we have some buttons. Clicking on this one, we open a plain plot. Okay. So what we want to represent is the proper motion. So we select proper motion and right extension and proper motion and declination. This is the proper motion of the sources. There are clearly the bulk of the sources are clearly concentrated around 0, 0, which actually are the sources in the in the background are field stars. And here we can identify another clear cluster of sources, which actually is the Pleiades cluster. So we are going to select these sources. Clicking on the third button, we can, with the mouse, just select the sources and create a subsample. Yeah, this is co-moving sources. Add subsample. Now the sources are represented in a different color. And also, if you go to the main TopCut window, on the seventh button is the subset button, and here we have information about this subset that contains 168 sources. Okay. So let's continue with the tutorial. The next is to from these sources which are moving together, identify which of them are in the background or in the foreground. So which are really belonging to the Pleiades cluster. Well, let's go with the fourth step. In this step, we are going to use the parallax to identify sources which are not at the same distance than the Pleiades sources. Even if they are moving with similar parallax, they are actually in front or behind the cluster. So with this, for this, we are going to create this histogram using the parallax tab. When you create the histogram, we can see that the parallax go from 0 to 70, and there is not a clear region where the cluster it is. And this is because if you go to the subset tag, it is because the comoving objects, which are those in blue, those that share the similar proper motion, are not plotted in this diagram. But now it's very clear the comoving sources has a very similar parallax as well. We can remove the rest of background stars and replot the histogram. And here we can see how there are the domain of the sources are centered around 7.5, but there are some sources with small parallax, which are background sources. One source with a clear large parallax, which is larger parallax, which is a foreground source. So we can create another filter to select only the sources which are in this central region. So in the, I will repeat this because I have gone very fast. Here in the main window, we click on the subset button, and we click on the plus symbol to create a new subset. And this new subset will contain, let's name the subset cluster, and will contain the sources in the comoving subset, and only those which has parallax larger than 6 and parallax smaller than 9. Okay, so here is the cluster sample, and we have removed 4 sources at the background, 3 sources at the foreground. Okay, this is the idea. We could do a more sophisticated refinement if you want. For example, we can create a Gaussian or fit a Gaussian to the data, and here we have the mean value, the standard deviation, and then create a filter that cut the data. For example, the mean plus 3 sigmas, 3 standard deviation, and minus the mean minus 3 sigmas, or whatever you want. So you have you can create the more sophisticated filters that probably are more strict filters than the filter that we have just created now. But this is just an example how to work with the tool, and is better to move on the next step to continue working with the data to estimate the distance to the cluster. So go. Okay, let's continue. Before continue with the next step, let me show you few. Well, one thing that I think is very interesting. We have identified sources that move together in this plot, and we have named it as comoving sources, and from these comoving sources we have identified those we have a similar parallax corresponding to the Parallax cluster, and those which has not. The blue one are the sources which are outliers in this diagram. Let me show the histogram diagram. No, those the blue sources are those which has a smaller parallax or larger parallax. If you want to know which actually are the sources, you can go to the plot, click on the source, and the source is highlighted in the main table. Go click on the other source, and the source is highlighted. Okay, so you can explore the data from your diagram, from your plot, going to the table, and also you can let me select the comoving sample. Only now the main the table with the data shows only the comoving sources. If we click on the table, the source appear in the is highlighted in the diagram. So you can explore your sources from the table to the diagram, and from the diagram to the table. Okay, I think this is very interesting. A utility from TopCat. So let's move on the next. We are going to continue with this, and in a column statistic, we open this window, and here we have statistics of all the different columns in the table. We have many different columns. Also, we can just in the column table, we can just select the table that we want to analyze, for example. So we have only the parallax and the proper motion, and here in the statistic we have the parallax and the proper motion. And select the cluster sample, which are the true members of the Pleiades cluster, and then we have the parallax and the standard deviation. So the next step is to do a new filter to select only those sources that has relabeled parallax. In this case, we are going to create a new subsample called good distance. Will be the sources in the cluster subset, and those that has parallax error divided by parallax smaller than 0.1. That means a relative error of 10% in the parallax data. So now we go to the statistic window, and we have the new statistic where few sources has been removed. Okay. We can also go to the histogram plot, and we have already added the Gaussian fit. We can select the good distance, and we have also the mean and the standard deviation, which actually is the same statistic. Okay, so we have now a clean parallax, and the next is then to analyze a little bit the data from our cluster. We have all selected the data, the sources from the cluster, and those that actually has relabeled measurements of the distance of the parallax. Okay, time is running faster than I would like, so I think that it's better to move on. There is no questions in the Slack channel, so I think that probably most of you have already used it Topcat before, so it's not new for you. So let's move on with the analyze. So the first thing we are going to estimate the distance. For this, clicking on the column button, we open the table columns and we add the plus a new column, which is distance. As the parallax is given in milliseconds, then the distance is 1000 divided by the parallax. The distance in parsec. Okay. So now we have defined the new column. Here we have the distance. And go back to the statistic window, and now we have the distance, which is blank, but we can recalculate clicking on this button, and we have the estimation of the distance. Siska means how to fit the Gaussian. I will show you very quickly. This is the histogram. Here we have the Gaussian. Actually, we can delete this Gaussian. Oh, this is this plot. We open. This is the parallax. Let's go Gaussian with the distance. Here we have the distance. We have the. Let's go to the good distance. So if you go to this case, you go to form, the third tag, you can add new form, and here you have the different options, and one of them is to add the Gaussian. And here at the bottom you have the value for the Gaussian, the parameters of the Gaussian. So again, more information about how you can obtain more information about the BO. Actually, if you go to the web page of the BO in education and outreach, you can find more tutorials, and also there is a YouTube video explaining this tutorial, but not exactly this, but a similar tutorial also in Spanish, but you can follow. The rest of the tutorial of Topcat, similarly as the Aladdin tutorial, I leave you to follow the tutorial by your own. And now we are move on VOSTA, which is the third data. One thing before this, you have worked with the table, you have created different samples. Even if you have different tables, not just this, but you have 3, 4, 30, 50 tables with different subsamples, each tables, you can save your data. You can save just the table, multiple tables in the case that you have more than one, or the session. If you save the session, you save the table with the subsamples. You don't save the plots. It's a pity, I know, but the plots are not safe in this. But you save the session, you save all the different tables with all the different subsamples. So next time you can open your session and continues working at the same point. Okay. So let's move to Bosa. Bosa. Let me. So Bosa is our tool that has been developed by the Spanish Virtual Observatory, and the main goal of Bosa is to analyze spectral energy distributions. Okay, so the first thing that you have to do is to go to the Bosa web page, which is this one, the one that I'm showing now, and you have to register. Hopefully you have already done. Now you have to do it just with the mail and your password and login. In your case, you will see only one possibility, the stars. The other possibilities are beta versions of the tool, which are being tested, but they are not public sessions. But this is the public session, okay, the public tool. Let's say. So there are different tags. The workflow in Bosa is very simple. Actually, we upload a couple of sources, then we search for the coordinates, we search for the distance, then we build the SED, analyze the SED, create the Hir diagram, and save the results. Very simple. And all this is just following the different tags in the web page. Okay, so it's very simple. We have the idea is very simple. We have the SED. From the SED, we can, using models, we feed the SED and obtain the volumetric flux of the source and the effective temperature. With the volumetric flux, if we have the distance from Gaia, we can obtain the luminosity. If we have the luminosity and the temperature, we can obtain the size of the stars and also the gravity of the star. So this is the idea. The idea is to use the power of the virtual observatory to build the SED actually. So let's start then. The first is go to the tool and the web page and login, and the second is to go to this to click on this on the link which is in the tutorial and download the file. Okay, I have the file here. No, here no. This is not here. It is in the here we have the file. The file is, where is the file? Here, the last one. This is the file that you have to download. Okay, let me show you this file. This is the structure of the file. There is not a couple of sources, there are 5 sources. So we have the name of the sources and just the three lines, another 3, which are just blank fields for Bosa. Okay, so Bosa will understood that each of these are a different source, and that is okay. So the next is to well, these symbols are corrupted. They are arrows actually. So go to the file, and in the file tag, browse, and go to the file where you have saved the file and open it. Write a description, whatever you know. Rosa School. And just upload. The file type, the unit of the data, you don't have to put nothing because it's empty. There is only the names of the sources, and just upload. Okay. So now we have the data here. We can show the object, and here we have the information. Position unknown, distance unknown. Okay, so the next step is to actually search for the coordinates. So I give you a couple of minutes and continue. Well, let's go to search for the coordinates. If we go to object, in the object tag, the next step is coordinates. So there is no coordinate for these sources, so we can search coordinates, and then you see this VOSI using the Sesamo service to identify the coordinates, or not to identify, to obtain the coordinates. Okay, so we have the coordinates. make all changes. Clicking on make all changes, the coordinate that has been are assigned to our sources. So we have the coordinates already. The next is distances, which is the next step, which is the same. Now we have the coordinates. We can go to different catalogs to obtain distances. So of course, the early DS3 catalog from Gaia is the main one, the catalog that contains most of the parallaxes, but it is not the only one. We have also the DR2, Digas catalog, and also all other catalogs previous to Gaia. So we search for distance. And we have obtaining the distance for some of them from the Gaia DR3. We have the sources, but there is no parallax. One of them, other is not in the Gaia DR3. So let's set the value, select the value by ranking, and put the Gaia visir first. And save the distances. And select, sorry, first make all changes and then save. Okay, so we have distances. The next step is to build the SCD. So I give you a few minutes while I'm looking at the Slack channel. Okay, let me answer a question by Chandra. He says, since these article identifiers and the Gaia collaboration has produced cross-matched tables of true counterparts, not just the nearest neighborhood to Tycho, does the Bosa interface still use consearch in this case? Yes. Yes, it using just a consearch to identify the sources. That is like the reduplication of effort. Yes, you are right. You are right. But what actually Bosa is doing is using the coordinates to look for data. Actually, Actually, all of these sources has Gaia counterpart, and there is one source that has not been identified in the Gaia EDR3, and I will tell you why. Okay, this is a little tricky. There is different services providing data from Gaia. Gaia, the direct ESA service that give you can do the cross match with ESA, and also the Gaia catalogs are in Visir. In the case of Visir, Visir has shift the coordinates, the position of the source, to the 2000 epoch using the proper motion. Okay, so this, if you are using coordinates from another epoch, you could have problems identifying or doing the cross match. So in the case of the ESA service, the coordinates are refers to 2016. In the case of the CDS service, the coordinates are refers to 2000. So sometimes if you cross match the same table in two different services, you can have different results because this. So in this case, we are using the Visir table at the CDS, or the Visir service at the CDS. Okay, but to understand exactly the reason to use identifiers when available. Yes, you are right, Sandra. Yes. But in this case, we are just showing the tool. So let's continue then with the next step, which is to build the SCD, because the session is running very fast. The time is running very fast. So let's build the SCDs. And I don't know which these symbols, this question mark are actually arrows, but I don't know why this is shown a question marks. But anyway, I think that you have realized from this. So let's unmark all of them. There are many different catalogs where VOSA will query for photometry. Just to do the exercise in a short time, we are going to select only few of the catalogs. Okay, so we are going to select Tomás, Denise, Kiko, the optical. So Tomás and Denise are the near infrared, Kiko the optical, Gaia, here 2, and Galax at the ultraviolet. Galax. And query. Okay, so now we have the information, and we can visualize the SCDs. So here we see the data and the SCDs from the different sources. Also, we can see all of them. Here we have the SCDs. Okay, you can see there are red points and orange points, and this is because, for example, here there is no orange point. Go to the next. Here we have one orange point and another one at the mid-infrared, and these are data which has been flagged as bad data for the catalog. So the NIS BOSA not only requests the photometry information, but also the quality flag of the data, and identify which photometry point has not good quality flags, so they are not used for the following analyze. Even they are shown in the SEDs, they are not going to be used in the analyze of the SED. Okay, so I think we are almost finishing the session, so I will reproduce the exercise. Continue with the exercise. In this case, we have to go to the analyze SED, okay, and we have different collection of models that we can use. Okay, of course, you have to know which model is suitable for your data. In this case, we are going to use the BT-settle, the first model, and also there are different possibilities. Chi-square fit. We can do a bias analyze. We can also use template to fit our sources, different template, or even do a binary fit. Binary fit is a SED produced by a binary star. Okay, so we have in this case, we are going to use two models to fit the SED. In our case, are single stars, so we just select the model, then select the parameters, and we are going to restrict the parameters from 4,000 to 7,000 Kelvin. Restrict also the gravity and make the fit. Okay, I restrict just the range of the parameters to do the fit faster. Okay, but you can leave the whole range, and then BOSA will take longer to reproduce to produce the fit. So here we have the data, we have the temperature, we have the, well, log G, I have fixed it, so it's of course the same, but we have the luminosity. In the case that we don't have distance for the source, BOSA use 10 parsecs as a reference distance. So for this, okay, we can show the different fits. The blue is the model, and the red are the observational data. Okay, and remember the yellow are bad data. The orange, yellow, orange. Okay. So the next step, build an Hir diagram. So those are going to use the temperature and the luminosity to build the Hir diagram. And in this case, yes, we are going to use these isochrons and continue to make the Hir diagram. Okay, so we have look at the Hir diagram that we have obtained, the luminosity, the temperature, how the two sources with bad distance are out of the range of the model, actually, but the other three are in the range of the inside the range of the models. So BOSA interpolate these three sources to give us the age and the mass of the sources to provide more information, more physical parameters. And just to finish, let's go to the results. So when you have already finished the whole workflow, you can go to the results and then download the data and save the data that you want to store in your computer. I have to say that if you have registered in the tool, in the system, and you have login with your user and your password, BOSA identify your session, so you don't need to do the whole workflow at once. You can do part of the workflow today, leave the session, enter the session tomorrow, and go back to this session and continues the workflow at the point that you finished today. So this is why actually you need to log into the system before start working, because BOSA identify the user and provide with the different session, the different works that the user have done in the tool. Okay, so you can retrieve all of these object properties, the SEDs, the fitting, the result of the fitting, and also let me show you your attention in the log activity. Fine. Actually, if you go to the log activity, here is the log of the different step. Talking about the reproductivity, here you have all the steps that you have done, so you can reproduce the session whenever you want. Okay, and also even give you the reference for the catalogs and the models that you have used, so you can include the reference in your paper. Remember the reference, the tools and the catalogs, everything is important in astronomy. So with this finish, the same, the tutorial contains other workflows that you can explore by your own. So if you are interested in the tool, just finish the tutorial with the other workflows that show you different utilities of the tool. Okay, so I think that we can finish this tutorial.
Okay, Fran, thank you very much. I don't see more questions. So I would like to thank again to the speakers of this session.